And that is work I did and I'm still doing with Dan Hoders, who works at the Naval Research Lab in DC. And what is different from this talk to every talk you saw in the morning is that I'm going to make an assumption that is not compatible with what you saw in the morning. So I have here a model that I assume is deterministic. It's just so I can more easily talk to my friends in the atmospheric sciences department. I don't think that the bulk of the talk and the results that I have are dependent on your model being deterministic. But that's my setup. We had a really well-working pointer in the morning. Do you have one?
I have a good one, but I'm going to have to advance separately.
Yeah, that's fine.
It's in here somewhere. I have to reverse the batteries because they're draining.
This one will work. Okay, I'll just start talking. So I have a model. K is discrete time, and I have a state at time x is the model applied to the state at time k minus 1. And then I have observations, and I assume that the observations are linear functions of the state. And that, I think, is an important, oh, thank you, that's much better. That is an important assumption. And I also assume Gaussian observation errors. And now model and observation jointly define posterior distributions. And I can define two. One is called a filtering distribution, where I make an update of the state at the observation time. So I have the distribution of the state at time k given all the observations at time from time 1 through time k. And I think in Dan's cartoon, those were the circles. There's another posterior distribution that I can define, which is a smoothing distribution. So I look at the state at time k minus 1, meaning one time step before I make an observation, and I condition on all observations up to time k. And both posterior distributions can be factorized into the product of a likelihood and a prior distribution. Now, numerical algorithms for data assimilation, meaning I want to try to combine the model and the observations to come up with a good state estimate, make use of these posterior distributions. And perhaps not surprisingly, filters work with a filtering posterior distribution, and smoothers work with a smoothing posterior distribution. And I take these terms pretty, I use these terms pretty broadly. So examples of filters are particle filters that Dan talked about in the morning, iterative ensemble filters that Mark often talks about, and also ensemble Kalman filters. And examples of smoothers are, you can also think of particle methods that solve this smoothing problem, iterative ensemble smoothers, or 4D VAR methods. And one example is an EDA scheme, which is ensemble of data assimilation, so I solve stochastically perturbed optimization problems. And the goal of all these algorithms is to use a Monte Carlo method or an ensemble approach so that you represent the appropriate posterior distribution, the one that you picked, by an ensemble in the hope that ensemble averages are equal to posterior means and ensemble covariances are equal to posterior covariances and so on. Now, if the model in my setup here is nonlinear, then you have non-Gaussian distributions that you can easily see. So I have here the filtering posterior distribution. It is proportional to a likelihood, which is the observations given the state, times a prior distribution. Now that prior distribution is obtained by applying a nonlinear model to some previous state. If this is a nonlinear model, then the distribution of this random variable here is non-Gaussian. So the logic is you have a nonlinear model, so you have a non-Gaussian prior distribution, and that gives you a non-Gaussian posterior distribution. And our common ideas are like this. Methods such as the ENKF and 4D VAR make implicitly or explicitly assumptions about the distributions here being involved here being Gaussian or the model being linear. Since I know that my model is nonlinear and I know that this whole problem here is non-Gaussian, I should be removing the assumptions of linearity and Gaussianity, and then I will get better forecasts. And basically the rest of the talk is about the question, is this really strictly speaking true, or is there a more complicated and more interesting story behind all of this? And I will try to first talk a little bit about how you can have Gaussian looking or nearly Gaussian posterior distributions even if prior distributions have more than one mode due to a regularization effect of observations. Then we'll talk about what all of that means for numerical data assimilation, and then show you this in action on the Lorentz 63 problem, where I don't need localization because there's 3 equations. And then if time permits, I'll talk about an experiment with a KdV equation where I do need localization. Okay, so here's a common statement. If I have a data assimilation problem and I have a large gap between two consecutive observations, then the problem is nonlinear, and the larger the gap, the more nonlinear is your problem. The more nonlinear and non-Gaussian is your problem. And you can illustrate this by looking at triangle plots. So those are histograms of every 2- and 1-dimensional marginal distribution of a distribution over the 3 variables of the Lorentz 63 problem. And I obtained this, so those are slices basically through a probability distribution. And I've obtained this one by sending 1 million samples of a Gaussian distribution through the Lorentz 63 dynamics for 0.1 time units. If I make 0.1 larger to 0.3, then I see that I have perhaps obviously more non-Gaussian looking distribution, because now I can see here in the marginal distribution over X 2 modes that are almost clearly separated. So it's hard to argue that going from here to here, the distribution becomes more non-Gaussian. And I actually don't care which characteristic of non-Gaussian you choose. Whatever choice you make, you will see that this is more non-Gaussian. Now the same is not true if you look at the corresponding posterior distribution. So now if I observe this state, I have a Gaussian prior, I observe this state at 0.1, I have a nearly Gaussian looking posterior distribution. And if I increase the time interval between the 2 consecutive observations, I also still have a nearly Gaussian looking posterior distribution. So
this only if H is linear, right?
Yes. So I said that very clearly in the beginning. I have a couple of assumptions. H being linear is 1. You were probably not even here. So it is true that posterior distributions can be nearly Gaussian, even if the prior distribution is bimodal. I showed you one example of this. So the question is why? And I can explain this pretty quickly on the example of the filtering posterior distribution, which is a prior, which is a forecast distribution times a likelihood. And I can write that as e to the minus f, where f is this thing here. And if f, the important thing here is to understand that if f is quadratic, then the distribution is Gaussian. And I see here a term that comes from the prior, so you have the model m in a couple different terms here. And this is probably not quadratic, because I have a nonlinear function here applied to x, and then I take the norm and square it. But I have a very nice quadratic regularization term that comes from the likelihood. And that, of course, relies on the observations being linear, as you pointed out. So if h is linear, or nearly linear, then I will have a prior distribution and have it regularized by a nice quadratic term in the likelihood. So you can maybe think about this as these observations regularizing your problem and making the posterior distribution more quadratic or more Gaussian looking than the prior distribution. The same also happens in smoothing problems, but it's slightly more complicated. So you can also write the smoothing distribution here as e to the minus f, and then you have actually, in this case, a nonlinear or non-quadratic term coming from the likelihood, and you have some other term coming from the prior. But in a smoothing setup, the prior of the current cycle is the posterior from the previous cycle. So if you actually buy into my logic, then this prior here is Gaussian or nearly Gaussian, because I showed you that on the previous slide. So then I might actually make a Gaussian approximation here, which is often done in 4D var methods, and then I can see that the regularization comes from the previous observations, because now my quadratic term here is from the posterior at the previous time step. Okay, so that's just a summary.
Sorry,
yeah.
In the previous slide,
Yeah.
do you assume that what you're doing is fixed lag smoothing?
Yes. It's just actually, it's even worse. I do one lag. Yeah. Well, my main point was here that the observations have a regularizing effect. I think you would also see that if you do different.
I understand that, but my question is that good? I mean, you're lucky that Lenny isn't here anymore, because he would kill you. I mean, if it's bimodal, it should.
Oh yeah. No, but okay. So wait. Okay, wait a little bit more. So my summary so far is just to make, I actually wasn't trying to advertise, also very different from other talks here, I'm not trying to advertise any particular numerical method. I actually don't care about what method you use. I just want to tell you about problems and what they look like, okay? So I have made an observation that posterior distributions, even in a nonlinear problem, can be nearly Gaussian. And now I want to think about what does this mean. Particularly, I want to define the degrees of nonlinearity in a problem by looking at and thinking about prior and posterior distributions. And again, to remind Peter Jan, this is all only true if these assumptions are true. So I have linear observations, Gaussian observation errors, and no modal error. I think the last one, because that seems to be a trend here, I think I could relax easily. The other one, I'm not so sure. So I looked again at the Lorentz problem and an old paper by Metref and others. It's a 2014 paper, I don't think you can see it. And they have defined mild, medium, and strong nonlinearity for the Lorentz problem in terms of the gap between two consecutive observations. So, and actually many people have told me that I should rename it in mild, medium, and spicy, but I can't do that because they call it strong, okay? So they said it's mild nonlinearity if delta t is less than 0.1, is medium if it's between 0.1 and 0.4, and it's strong if it's bigger than 0.4. And now if you try to define mild, medium, and strong nonlinearity in terms of distributions, prior and posterior distributions, then you can see in a mildly nonlinear regime, all the distributions that are floating around, that is prior distributions and posterior distributions, are nearly Gaussian. If you go to the medium nonlinearity regime, then you have possibly bimodal and not so Gaussian looking prior distributions, and still kind of Gaussian looking posterior distributions. And if you go to the regime of strong nonlinearity, you can have very strange looking prior and posterior distributions. So here you see a particular slice of the Lorentz system where you have two modes, and possibly people would start yelling at me in this regime. Okay, so now if I want to solve this problem, or this problem, or this problem, I should probably use different numerical techniques. So I want to think about what numerical technique should I use in which, for which type of problem. So again, I keep saying the same thing. Mild nonlinearity, all distributions are nearly Gaussian, so I can probably get away with Gaussian approximations of prior and posterior distributions. In the medium nonlinearity regime, I should not make a Gaussian approximation of a prior, but I can make a Gaussian approximation of a posterior distribution. And in the strong nonlinearity regime, I should not make any Gaussian approximations. If I want to create an efficient numerical technique, I should make use of the fact that some distributions in some of these types of problems are Gaussian, because I will get more efficient numerical algorithms. So in this case, when a Gaussian approximation is appropriate, it's not a bad thing to make a Gaussian approximation. So if I look at the different numerical data assimilation methods, an ENKF implicitly, I would argue, makes a Gaussian approximation of the prior. A variational scheme, very broadly defined, makes a Gaussian approximation of a posterior distribution, and the particle filter makes no Gaussian approximation. So if I go to a problem of mild nonlinearity, ENKF and 4D var probably should perform very well because all the approximations that are done are valid and good. The particle filter will also work, but probably will require a larger ensemble size than an ENKF because it doesn't make an appropriate but simplifying approximation of a Gaussian prior and posterior distributions. If you go to medium nonlinearity, you will probably see that the ENKF will start to suffer because it makes an inappropriate Gaussian approximation. But 4D var will remain to be effective because it relies on a different Gaussian approximation of a posterior distribution. So this will be a good method to use. Again, I can of course use the particle filter, but in that case, I will again probably require a larger ensemble size than when I use methods that make appropriate Gaussian approximations. Once I am in the regime of strong nonlinearity, I will need to use a particle filter because none of my Gaussian approximations are valid anymore. And then I'm in the regime that you mentioned where I have possibly two modes. And if you want me to solve such a problem, I would also argue with you that you need to allow me to use a larger ensemble size because I would not be able to properly represent more than a handful of modes with a small ensemble. And also, if you try to estimate the skew of any random variable with an ensemble size of less than 500, you pretty much get a random number again. So you can type that into Python or Julia or whatever language, or Google, I guess. So once you are in this regime, independently of any dimension issues, you will need a larger ensemble if you want to solve this type of problem.
Yeah, but Matty, you know, it's not, I mean, with the iterative ensemble, you know that, but the iterative ensemble filter and smoothers, I mean, you're good with that. This is the only choice, reasonable choice that you can make with strong nonlinearity.
I would put that in the medium nonlinearity regime.
It goes up to 0.6, which is beyond the regime that you define. And it does wonderful results for 0.6, then it starts to be more difficult beyond that.
Okay, I'll show you. Okay.
With the standard value that you described.
Okay, look. So here is, I think you will see, I think you will see right now, okay? So I'm going to keep using that setup of Metref and others from 2014. I have relatively large observation errors, and I vary the time interval between observation from 0.1 to 0.6. Other questions? No? And as I increase dt, I go from mild to medium to strong nonlinearity. So that's exactly the case that is discussed in this paper. And then I apply the ENKF, variational method, and a particle filter. And I do not apply the iterative ensemble comment. But this is what I show you. I show you another set later, okay? And then we tested this. And then I don't think I need to talk in this room about why I use Lorentz 63. Okay, I need some baseline solution, and I don't even want to get into localization. Okay, and you can see the following. You can see that what I said before is it might be correct. So in the mildly nonlinear regime, the three method that I'm testing here perform similarly. Then once you transition into the medium nonlinear regime, you see that the ENKF, not the iterative one, starts to give you a larger RMSE. But the 4D VAR method keeps giving you a solution that is almost as good as the particle filter. And then once you transition into the strongly nonlinear regime, you see that both methods, the ENKF and the 4D VAR method, are giving you a large RMSE, and only the particle filter gives you a smaller RMSE. Now the problem is I plot RMSE, which I think was said in the morning that it's not reasonable to plot RMSE if you have a situation where you have a distribution that looks like this. And that I think is absolutely true. Those are averages of RMSE over 1,200 cycles or 1,000 cycles, something like that. And this situation actually happens relatively infrequently. So even if sometimes I make a bad, it's inappropriate, but sometimes for many of the cycles, actually an interesting thing to look at. So besides issues with RMSE, I think that this shows you that maybe what I said before is what I said before is true. You can also see that once you transition to more difficult problems, you will have to increase the ensemble size. So here I plot the required ensemble size of a particle filter as a function of the degree of nonlinearity, or the interval between two consecutive observations. And the required ensemble size is defined by comparing to a particle filter with ensemble size 1,000. And once my particle filter with a smaller ensemble size, the RMSE is similar to the one with with an ensemble size of 1,000. And you can see that that increases. So if you want me to solve a strongly nonlinear problem, then again, I want to iterate that again, then you'll have to allow me to use a larger ensemble. I cannot solve a problem of this type with 40 ensemble members.
Yeah. About the standard particle filter with no tempering, no nudging, no additional.
No, I'm talking about, so if you give me a complex looking distribution of this type, let me show you a good example again. Where is it? This one. So if you ask me to get your represent, even in 1D, I wouldn't want to do this with an ensemble of 40. I want at least a couple hundred.
Wait, are you allowed to use nudging and tempering, all these things?
Yeah, just any random variable, if it has some complexity of this type that you have more than one mode, I don't want to deal with it unless you allow me to use an ensemble size of a couple hundred. Because so.
With 40 members, you can represent with 2 peaks. There's not a problem.
In one dimension.
Yeah, I don't agree. As I said, type into Google skew of a random variable and compute that from an ensemble of 40. And you will get another random variable. Yeah. So if I'm interested in non-Gaussian behaviors, maybe I'm interested in this skew. And then all I can tell you based on an ensemble of size 40 is, I don't know. So I would ask, please allow me to use a larger ensemble size. Okay, so I'm happy to talk about this more. I think it's okay to ask for more if you are solving a more difficult problem. Now let me get back to Mark's question with the RMSE and the spread and how things are going south once you're in this regime. So I have not shown you the error for the iterative ensemble Kalman smoother or iterative ensemble Kalman filter. But somewhere down in my backup slides, there are similar methods that we tested. And we saw them giving us larger RMSE in the strongly nonlinear regime. But mostly because the optimization algorithm that we ran did very poorly. And not only when we saw two different modes, but also sometimes when we just saw one mode in the posterior distribution, it just it didn't succeed. So it's possible that if you do an iterative ensemble smoother, you implement the optimization more carefully, and it might allow you to go into this regime once you are faced with a truly bimodal. Where is my? I should have that.
It's true when the Gaussian approximation is not satisfied anymore. It's true that this is in the optimization that you will see.
Yes.
So that's not what you're saying. It's consistent.
Yes. So your ensemble, iterative ensemble Kalman smoother might find an optimum that is here, but you will have a true state that is here, and then you will have a large RMSE. So that can happen. Okay. Okay. I have a few minutes, right? Now, last time I gave this talk, Andy might have wanted me to stop before this because he said it's not a good test problem. So it's a KDV problem with variable coefficients. Might not be the most interesting PDE you've ever seen, but at least it allows me to go to dimension 128, which is larger, and it requires me now to use localization. Before I didn't use any localization, I just used inflation. Now I also have to use localization because otherwise I don't get anywhere with any data assimilation technique. And it's a nice problem because it has a relatively low dimension. I can still run a brute force particle filter with some jittering, actually, to look at this. And then I can look at localization of the particle filter and effects that that has on it. So we tried John Potterjoy's code. Did not work very well. If you talk to John, he has new iterations of his algorithm often, and I don't doubt that he has fixed this problem. This was a problem where you have small observation errors, and his code doesn't work very well there. Probably has a new version by now. We also tried a German weather service-like localized particle filter, which is basically a standard particle filter, which you have determined. What do you call it usually? You had another word for the standard particle filter at some point, but anyway, standard particle filter. Huh? No, I think it was more evil. And it has an LETKF style domain localization. So you compute weights at one grid point, and you resample there, and I do that just independently. I'm not claiming that that's the best localization technique, but it's also reviewed in Mark's recent paper on localization. Is that correct? Yeah. And it can...
Tekimasa is a very nice one with
yes.
But it's not...
Well, so of course, if I try to compare a bunch of things, there's always more. I want to just make one point. So I use that localization technique, and at this point I forgot which... Okay, so this one is the particle filter with localization, and this is the ENKF. And you see that the localization made a larger error than a Gaussian approximation, because this is a problem that happens to be in the medium or mildly nonlinear regime. So that can probably be fixed if you do the localization more carefully. But what I want to say is that once you have to use localization in a particle filter, there's a whole other source of errors that can happen, and they may be more important than errors that you make due to more or less appropriate Gaussian approximations. So once you get into that regime, you might want to think about this carefully. So let me summarize really quickly. We have define these regimes of mild, medium, and strong or spicy nonlinearity in terms of properties of prior and posterior distributions, and then could think about what that means for the applicability of various data assimilation techniques to problem in each category. And then I think that those are partial answers to why you often see that it is difficult to build an algorithm or a particle filter that is better than ENKF, because many of the test programs we use are mildly nonlinear, and in that case you have nearly no chance to do better than that algorithm. If you compare your particle filter to variational methods, then you also will have a hard time unless you go to the fully or strongly nonlinear regime. And it's also a partially an explanation of why you often see that variational data assimilation does better than an ENKF, because many test problems, or perhaps many problems, are in the mildly nonlinear regime. So that's something I want to think about. Are those results only due because we're stuck on some limited set of test problems that are all in this regime, or is that really true? So unfortunately, I have no answers to these interesting questions, which is numerical weather prediction actually strongly nonlinear? And what effect does it have to actually properly assimilate the nonlinear aspects of weather, and what effect does that have on forecasting? And another story that is often told is, if I increase the resolution of my model, then I have more nonlinearity, and then a particle filter will be necessary. It's possible that that is also a more complicated story, especially if you think about simultaneously increasing also the resolution of your observations, because that can then keep regularizing your problem to remain the mildly non-Gaussian or nonlinear regime. And this is all I have. And this is an animation of the filtering prior and filtering posterior over the 1,000 cycles in the Lorentz problem. And you can count the number of times you see two modes here, and I think it's only 5. And you can, this looks pretty, this can often look pretty nasty.
Thank you.
Yeah.
Okay, we have time for 1 or 2 questions. Mike.
Thank you, Matthias. It was very nice. Very nice. Could you spell for me, because maybe it is clear to everybody, but I don't understand very well why you say that variational method generally rely on assuming that the posterior is Gaussian. For this to happen, to my understanding, you need also to make the assumption that both observational and prior error are Gaussian, so that the posterior will be Gaussian as well.
Yes,
I don't understand how this split counts at the very beginning.
Yes, so let me... Unfortunately, in the case of everything is very clear for the filter, and then everything becomes a little bit more complicated in terms of the variational method. So you have this nonlinear term here that comes from the likelihood, right? There's the model, this is the observation operator, that's the observation. And then there is some term of a prior, and that is often assumed to be Gaussian. So you may have a quadratic term here. But if you look at how the filter and smoother are set up, this prior distribution is xk minus 1 given y1 through k minus 1. So that's a posterior distribution of the previous cycle. So in that sense, because you make a Gaussian approximation here, in that sense, the variational method makes use of a Gaussian approximation of a posterior distribution of the previous cycle. That makes sense? Yeah.
Okay. Yeah, so let me put on again my Lenny Smith hat or ponytail or whatever. So what if what you're really interested in is a non-Gaussian posterior, prior, everything? If that's what you got.
Well, if that's what you got,
yeah,
then I'll ask you to give me a large ensemble, a big computer, and a particle filter.
Okay. They're free for the ask.
Yes, Matthias. Thanks. I think it was an excellent talk, and actually I can relate to most of what you've shown from a global NWP perspective. I would actually say that from our experience, yes, I mean, we assume that the B is the initial covariance, the background covariance is Gaussian, and that relies effectively on looking at certain scales. So if you go down in resolution, and if you look at smaller and smaller scales, then nonlinearity and non-Gaussianity will start appearing.
Yes.
And that's effectively what limits us in the sense of what kind of scales one can reasonably analyze. Because if you don't do that, as we were not doing for a period, you could end up in a situation that, for example, your ensemble of EDAs had a non-Gaussian forecast of, say, the position of a tropical cyclones, one place or another place. And your posterior EDA had some of the members in one place, some of the members in another place, and some of the members actually two tropical cyclones, which is a situation that you would like to avoid.
Yeah, as I said, so I wish I had an answer to these NWP questions, which is also about what happens when you increase the resolution, which is difficult to test with any of the test programs that we currently have. I can't increase the resolution in Lorentz 63 or Lorentz 40, so then we might need to think about that test problem also.
Okay, I'm afraid we're going to have to leave it at that, move on to the next speaker. Let's thank Matthias one more time.